Hey folks, welcome. I'm Smitty, and this is my little home lab here. And today we're going to be talking about automotive computers. So when it comes to desktop machines, a lot of you are probably familiar with something of this nature, maybe a little Dell Optiplex. This one happens to be a 7050 Micro. And you probably see them, you probably punch in on them, you probably do spreadsheets on them, emails, whatever. Whatever it is that you do on a desktop machine, that's a computer to you, right? And maybe many more of you are probably even watching this video on something like this. This is a Samsung Galaxy S8 Plus. Obviously, it's older, but this is a phone, a mobile phone, and these have Qualcomm ARM instruction set processors. Now, what's important with that is that they are reduced instruction set, and they're made for, power efficiency and just general usage of heat is better, and they're pretty fast. They're a good little processor. In a vehicle, we kind of need the same thing. We need something that's robust and durable, but it doesn't take a lot of power, but it's still fast enough to do exactly what we need it to do. So say you hop in your vehicle, you're not going to be filling out spreadsheets on the dash of your vehicle. You're not going to be plugging in the seatbelt to check your emails, and you're not going to be shifting gears to scroll through Instagram. It's nothing like that. The computers inside your vehicle are a bunch of little modules or ECUs throughout the vehicle, and they have all sorts of different purposes. And here's today's example. This is an occupant restraint controller out of a vehicle from about 2014, and this thing is in charge of managing the airbag system. And one thing to note before we go any further, this has a giant capacitor in it, and these store a charge, and sometimes they can really bite you. So what I did was I hooked it up to the multimeter just to verify, of course, that this is completely discharged and we can handle this safely without shocking ourselves. So the way that our occupant restraint system works, or sometimes it's called the supplemental restraint system, it has a series of sensors in it, some rollover sensors, and of course some crash sensors. And these are usually set in such a way that if there's an accident that's been detected, it closes a circuit, and that way it knows that, hey, there's something going on, and there's going to be some further steps before we activate an airbag, and that's what this guy's in charge of. So on the surface, it looks like we could actually just take it and make a switch out of our crash sensor, right? So if the switch closes, it'll allow our power to go through and activate the airbag, which is hooked up to ground. And of course, if we don't really want to just set off the airbags all willy-nilly, we can just have one of our switches, of course, be for the crash sensor, and then add another one into the loop too. So that way we know for sure off of two sensors that it's trying to allow current. So on the surface, that looks like a good idea, but unfortunately there's some problems with that. There's actually quite a few problems with that. First and foremost, airbags are dangerous. They are an explosive device. That's how they work. So the way that the airbag works is it's a bag, and behind it there's like what's almost like gunpowder, and when we activate it, it sets off the gunpowder and inflates the bag so fast that it's going to be completely open before the driver even gets a chance to snap their neck forward, or what it'll do is it'll also pull the seatbelt right up to you and lock you right to the seat before you even have a chance to move. And because it needs to happen so fast, that charge, that actual explosive charge that's being put out is quite strong. And if it's not activated correctly, it can actually do more harm than good. Which, another thing to keep in mind is service and repair. When we're working on these components, there's going to be a technician working on them, a mechanic like me, that's probably going to be hunched over that wheel trying to get plastic off for the dash, trying to get the wheel off to get a clock spring taken apart, trying to get a steering column out, whatever it may be. There's going to be situations where there's going to be people over top of an airbag in a situation that normally wouldn't happen on the road. And also we need to be concerned with electrical failures and diagnostics. And this is a really key part of modules and how they work. So if we have an electrical failure, it can throw a code, it can at least try to log it in some way that we can look at it and determine what direction we have to start diagnosing in. And on top of that, we can disable the airbag system with a fault code. So that way we know we're not going to be activating an airbag in a situation that's unsafe. And of course, not all modules have the same mindset as this thing. Of course, we'll have like emissions, and we'll have engine performance, and there's other stuff involving modules that is important to us. But in this case, this one's more about safety. So let's take a closer look at this thing. This thing has an ST microelectronics processor in it. These are the specs for this particular processor: 32-bit accumulator, 32-bit barrel shifter, and a 16-bit multiplier. So what does this stuff really mean? Well, it's just how the processor is going to be able to handle some numbers, and that's some stuff that we don't necessarily need to worry about right this second. And for our power input, we have this little Infineon chip. They used to be a NASCAR sponsor right here. This is going to be doing our automotive power supply for this module. And this guy here is an NXP SX chip. It was likely more of a Freescale chip when it was manufactured back in 2014. So this does like packet-based data transmission, and it would be good for like ADAS stuff, but that's out of the scope of this video. And this little guy is who we're interested, because this does CAN communication, and we're going to be talking about that in this video. So CAN, or Controlled Area Network, is very important to how these bad boys work. So instead of doing it kind of like hot-wired like the last one, now we have an ORC, and what we can do is take our sensor data and process it before we do anything with our airbag. We're still hooked up to power and ground for the airbag, but what we have here is a couple data lines that we can send data on. So when it comes to our sensors, we can program the module to take input, like for example, like we had 2 or more sensors have to call a crash before it can activate the airbag. So for redundancy, we have our 2 or more rule. We also have what's called a shorting bar. So on connectors for airbags, typically if you were to take a connector out of a sensor, it has a little shorting bar. And what that's going to do is that's going to go back to our diagnostics. It'll determine there's a short circuit, and it will immediately disable the airbag system rather than setting anything off. So the one thing to be really cautious with is these rollover sensors. I haven't seen the greatest programming on those for redundancy. I've seen guys doing, let's say they're doing parking brakes on something, and the center console has the ORC module built into it. So if you were to remove the center console, the ORC shifts, and a lot of times the rollover sensor is on the ORC. So now that you don't have the center console straight up and down because you're trying to remove it, it wants to set off the airbags. So be sure to disconnect the battery and let the car sit for a couple minutes before you even try to touch anything, especially when it involves airbag stuff. So essentially, now that we have a module controlling a lot of these inputs and outputs, we can add more features than we actually thought we would be able to have. So we have more features than we have components, which is nice because that kind of gives us a little bit more tools to work with when we have something to control all of these parts and pieces. And like that shorting bar I mentioned earlier, also if we have like an error in the system and it is able to track that and disable the airbag system, it can set a light on the dash just to let people know, hey, your vehicle has an issue, you should probably bring it in for service. A lot of times they even have messages coming across where your dash panel is on a lot of the newer cars. So really, how does this little box work? I mean, it looks a lot like this is a Beagle board, or you could compare it to a Raspberry Pi, any little development board. But what I really like to compare it to, especially since this is a lot older, you can think of this as kind of like a newer version. This is almost like a blue pill. This is a ST microelectronics development board, and I have, of course, our little ST link here hooked right up to it. So when your mechanic plugs his scanner into your vehicle to check for codes and stuff, well, that plug can also be used for programming the car, programming these little modules in most cases. Not all cases, I have to kind of mention that now because there's a lot of updates over the air that come through on like 5G or even just on a phone line kind of thing. And how these work is eerily similar to how these development boards work. You flash them, the program is stored right on the machine, and in this case, I have this one plugged into power, and anytime it's powered, this LED blinks. That's all it does. That's all this thing is programmed to do. Of course, there's a lot more that can be done. Of course, these little holes we could solder some sensors to, and we could get more data and process it and keep looping it. It's kind of its own home-brewed real-time operating system. And that is almost exactly how our automotive boards work. You program it, it holds that program on the machine here, and it just simply loops it and keeps trying and looking for more errors or looking for the right data in order to get to the next task. And back to programming it, if you really just substituted this USB with an OBD2 plug that you would find on any modern car, it really communicates similarly, I can put it. Where these are going to be using like a UART or maybe even like a JTAG or whatever. I'm not really the best with these. These would actually be using controlled area network, and we could show you how that works because it is a little bit different than this, but we'll go into that here in a minute. So let's take a look at what's going on inside. This is a super simplified version, of course. So we're going to check our sensors, we're going to process that data, and if it's all right, we're going to go right back to checking our sensors. Keep on doing it. If it's not okay, we're just going to keep on going to set error. So if everything's okay, it has to jump back. If everything's not okay, it's not going to jump, and we're going to set an error. We're going to disable our supplemental restraint system, and then we're going to go back to checking and see if anything's fixed itself, which is usually a no, of course. Things don't fix themselves, but here's how it stores the data, zeros and ones. This is all kind of malarkey. I just made this up. None of it's actual binary, but so let's say our first instruction is something like this. That's what it does, and then it's going to jump down to our next instruction, which is stored in the next memory address. So it's just working off of zeros and ones, going through its memory and seeing, what it has to do and executing that instruction. If for whatever reason we find that there's a better way to go about it, we can reprogram it, update to the newest software level, and we're good to go. Or so we think, of course. Well, this isn't going to cut it. We actually have to talk to other modules and see if what's going on in their world is okay for us to execute what's going on in our world, right? So let's say we have our SRS hooked up to the BCM, our body control module, which is very common. The BCM has a little bit higher priority than this module, and we need to send some data. Like maybe it's sending data back and forth just to make sure everything's okay, or maybe it's found a problem and it doesn't want us to continue performing our program. So how exactly are we going to send this data? Because we make it nice and easy here with our little microelectronics that we have a USB connection, and in a car it's a little bit different than that. So in a vehicle we talk through CAN communication, which is a controlled area network. The way it works is it uses two different lines. That's it. So there is a CAN high and a CAN low. The way these two wires work is CAN high is at something like 2.8 volts and CAN low is at a different voltage like 2.6. This is a 0. And let's say our CAN high matches our CAN low and they're both 2.6. That's a 1. So those zeros and ones from before, this is how we're moving them around. And let's say our CAN high, it went down in voltage to 2.6, which we know is a 1, so it's trying to send a bit. A certain amount of time goes by without any voltage change, so there's a good chance that this is a 0, and then we go again with another 1. It drops down again. And this is on a graph over time, and it's sent in serial. That's what's important about CAN. It's taking every bit one at a time, and it's registering it to our processor like we were showing before with the program. It's just adding that into its memory. Or in some cases, it'll go directly to a register to be processed, but that's kind of beyond the point. So CAN works on these serial inputs and outputs, and it can be really useful to communicate between modules. But I'm not done yet. It gets a lot more complicated than this. The way that CAN is configured is on a bus. So there's only those two CAN high and low wires that we're worried about. we're not going to send wires to each and every module. That's absolutely inefficient, and it's just not, it would be way too complicated. And this only works for a short range, so you're not going to be sending this through like a data line to another state. But it is on one bus, and they have to know who the message is for. Because before, our ORC was talking to our BCM. Well, let's say we have the powertrain control module on this bus as well, and there's going to be, of course, others. But if we just want to send between these two, how are we going to do that? So how we're going to do that is we're going to send a header out on that bus. And that's going to send an 11-bit or maybe even a 29-bit message on the bus that lets everybody know, hey, I'm about to talk to, let's put our CAN ID out there. So let's say we were trying to talk from the BCM to the ORC. We're going to put out a CAN ID that matches the ORC. So the ORC knows, hey, I'm about to be sent a message, and in this header there might even be some information on the message length, and of course maybe something to do with the contents, if there's a flag set, if there's some sort of something we need to know about the message before we actually read it. And kind of going back to message length here, we need to know the message length because in that frequency we showed drawing it out with the can dipping down and showing a 1 value. Well, there's no way to tell if a 0 is a 0 or if no data is being sent. So that's why we need to know kind of like a time frame of how much message there is. And there's certain intervals, of course, for frequencies that the module is going to know, hey, this is a 0, or hey, nothing's being sent. And so since we have the ability to send those headers out, we can send like a handshake, right? These are capable of the X in handshake, the 3-way handshake. So let's say we wanted to acknowledge somebody, like say we're the BCM again, we're trying to talk to the ORC. So in our bits here, maybe this bit recommends that we're trying to acknowledge somebody, and here's the ID for the module behind it. So that 11-bit number, like I was talking about earlier, actually has some information on how we're supposed to be talking to people. And then afterwards, our ORC says, hey, okay, that's my number, and I'm all right with sending information back and forth to you. It'll set this synchronize flag. So maybe that's a different number. Maybe we'll set this 0 to 1, and it'll send back the number with the BCM's ID rather than our ID. And then once we've done that to each other, both of those modules know, hey, we're actually talking to this other module. So we can say, we have acknowledged and synchronized, we can keep talking, and that'll be like another flag or a couple flags knowing who we're talking to and that we've already connected to them, and here's the data we're sending. And another big concern is dormancy. So what if one of these modules doesn't want to talk? It happens all the time. It's called a dormant module. And let's say our ORC is experiencing like a short, it has detected a short, and it doesn't feel that it is safe to operate, and it is going to take itself right off the bus and shut itself off. Well, it'll get this ACK message come through CAN, but it'll never have a synchronize come back to the BCM, right? So that way we know, hey, we can't communicate with this module. We don't exactly know why, but we know that it's not sending its synchronize flag, so we can toss that one down as dormant. We can't communicate with it. And so what'll happen, the ORC is going to keep running its tests. Say there was a repair made, and it finds that it's okay to communicate again. A lot of times it'll require a manual reset with the technician working on it. But of course, there's going to be situations where the module isn't going to want to talk, and you have to make repair about that before it wants to get back on the bus and communicate with the other modules. And it's about really all I have for you guys today, but what I really want to leave with you guys is, we have these really nice little RISC instruction set processors. These are reduced instruction sets. This one's particularly ARM. This one is also ARM. There's RISC out there. There's MIPS. There's all sorts of different ones. And they take a certain amount of power to run, a lot less than our Dell Optiplex than we were showing earlier. But what I want to know is is there a better way, a more efficient way that we can actually run these things? Because this is technology from the 90s, folks. I mean, seriously, we even have pins, just like we have pins on something like this, or pins on even our Beagle board has some spots. You know, like this is old school. We need something that's a lot more efficient, and the reason why I say that is because I've been working with vehicles that are draining their batteries so fast, it's not even funny anymore. I mean, it takes like a quarter of your house. Some of these things are running 29 amps with the key on, so you just can't leave your key on for any amount of time, or else you're going to be paying $300 for a battery, which is not fun. So just, I don't know if there's a better way to do this. If there's a way we can make it more like an actual computer, because there already is Ethernet in cars, and I don't really want to touch on that right now. I want to research that a little bit more before I talk about it. But I feel like Ethernet would be a better option in most cases, especially with the amount of data that's starting to be sent between these modules. But I want to leave that with you guys. I want to know down in the comments, like, what would be a better way to go about this rather than the old school CAN setup, or maybe even the old school ARM setup. Maybe we don't need a module everywhere. Maybe there's another way to do that. We can have little terminals all around and have one large processor in the middle or something. Let me know. Let me know what you think.